All right, kids, we're going to review measurement math. All the problems we're about to do from, it looks like number, I think 101 on, should be relatively easy for you to do because we've gone through all of this. You've hopefully done all the homeworks and checked them, and if you had any questions, you would have asked me about them. You've done the significant figure handout, and if you had any questions, you would have asked me. You've hopefully completely read the basics, and if you had any questions, you would have asked me about it. So basically, you should know this, all of this. And if you struggle, and that may happen, you need to do the problems again. When you want to be on a baseball team and you want to be the star hitter, you have to practice hitting, and you have to practice tomorrow, and you have to practice the next day, and you have to practice yesterday. And the more you practice, the better you hit. Chemistry is just like baseball. It's a good line. Chemistry is just like baseball. The more you practice, the better you'll get at it. You can do the problems over and over. It's not so much about getting the right answer. It's about recognizing what kind of a problem it is and what process you should take. If you're a baseball player and there's a runner on first and you're playing shortstop and it's a ground ball to you, with enough practice, it becomes automatic to throw it to the second baseman, and the second baseman throws it to the first baseman for a double play. That's really hard to teach little kids because they don't have the brain capacity. You're big. These problems, even if you repeat them over and over, you'll become more automatic with them. You won't spend so much time wondering what the heck should I do and getting yourself nervous. You'll just know how to do them. Practice makes perfect. So here we go. Number 101, convert this big number of milliliters into gallons. Now, probably don't know how many milliliters are in a gallon. I don't know how many milliliters are in a gallon, but I do know about milliliters and liters. And look, in parentheses there's liters into quarts. And hopefully you know that it's 4 quarts to a gallon. So our starting point, we put the starting point over 1. It's going to be 2450 mLs over 1. And now the first thing we're going to do is we're going to get rid of the milliliters. We make the conversion factor 1,000 mLs in the denominator and 1 liter in the numerator. Now we have to use the units because if you switched it and put the milliliters on top and made it 1,000 mLs over a liter, that still equals 1, but now the units don't cancel and the answer is going to be completely wrong. And the units will be wrong too. Make sure the units cancel. So when you cross out the milliliters here, we have liters. The next step will be go from liters to quarts. And then the next step would be from quarts to gallons. Make sure you cancel your units as you go. I'm stalling now. You should be doing the math. You might want to hit pause and do it because on the next slide are going to be the answers. Don't let me go too fast. You're in control. Press the button. Pause. I'll just drink some seltzer while you're pausing. Watermelon seltzer in the morning. All right, next slide. Look, here comes the answer. The milliliters cancel. The next step, like I said, was liters and quarts. We cancel the liters. And the last step, 4 quarts is a gallon. When the unit that you want, in this case, we want to convert to gallons. When the unit you want is in the numerator, put the equal sign and do the math. And when you multiply across the top, you get 2,597. And when you multiply across the bottom, you get 4,000. And when you do the math, you get that number, 0.64925, but we have to round it to 3 significant figures. So it's going to be 0.649 gallons with 3 significant figures. This is called dimensional analysis or unit conversion math. 2,450 milliliters is exactly equivalent to 0.649 gallons. Now, again, this particular problem, this individual problem, there's no sensible reason to convert from milliliters to gallons. This is a process. We will use this process to do conversions that will have more value to us later on. This is still the beginning. This is math theory. How are we going to learn math to do chem? We can't do chem yet. We're not really going to get to chem for a while. We're going to warm up. Even once we finish measurement, we're going to be talking about, I got to postpone something. It said it wanted to update my Windows. I don't know what happened. This is just practice. This is the beginning. This is the very beginning. This is learning how to catch. You're not playing baseball. You're learning how to catch still. All right, 102. How many millimeters are in 1,000 yards? And then you have to change to scientific notation. Now, a millimeter is super tiny. And a yard, you know, is 3 feet. Yard's pretty big. In 1,000 yards, that's a lot of yards. That's pretty far. It's going to be a lot of freaking millimeters in that. What do we start with? 1,000 point yards over 1. And that has 4 significant figures because of that decimal. So we start like this. Now, we have to get rid of yards and go to inches. And hopefully you remember that there's, in an inch, there's 2.54 centimeters. I didn't give you that hint, but that was in the notes earlier. And I told you you'd be a good person if you remembered that. So we start out with yards over 1, 1,000 yards. So we see that the yards is in the numerator. It is in the numerator, that unit. But now we're forced to see it, and we realize the yards has to go in the denominator for the conversion factor, and inches is in the top. Then we're going to go from inches to centimeters and centimeters to millimeters. And here we go. There's 10 millimeters in a centimeter, of course. When you multiply these fractions, first of all the units cancel except for millimeters. When the unit you want is in the numerator, slap on your equal sign and do the math. Multiplying across the top, 914,400. On the bottom, it's just 1. I didn't even write that. And so we have to convert this with 4 significant figures to scientific notation. Now, the decimal point is after the 0 and before the mm in 914,400. But there's no decimal point. We know it's there, but it's not written, because if the dot was there, we'd have 6 significant figures. We only have 4. But we have to move the decimal from the right side of that 0 back to between the 9 and the 1. And we're going to move it 5 places. So if we make the coefficient 5 places smaller, 5 times 10, 10 times 10 times 10 times 10 times 10 smaller, we have to make the exponent go up an equivalent times 10 to the 5th. All right. I like writing questions like this because otherwise you wouldn't believe it. You have a special moment and discover a hunk of metal in your backyard in the dirt. And it's stamped pure osmium. Osmium is an element on the periodic table, right? OS. It happens to be the densest element. So if you happen to hold osmium, a chunk, equal chunks of any other element in the universe would not have as much mass. Osmium is dense, it's heavy. And this osmium says 100 point grams. It looks really new, so you believe it's the real deal. You believe you have exactly 4 significant figures, 100.0 grams of pure osmium. How big is that piece of metal? What is the volume? This is a hard problem. You don't even have all the numbers, but you do. If it's osmium, it's on the periodic table. It's on the periodic table, it's on table S. If it's on table S, you have a density. You have density, you have mass. What you don't have is volume, but you do have a formula. So write the formula for density and let's get started. The density formula, density equals mass over volume. In this case, the density of osmium from table S is gigantic at 22.587 grams per centimeter cubed. And that's going to equal 100 grams over V. Now, some of you are going to be doing this triangle business. I can't help you with that, but this is how I would do the math. Now, what I did on the left side is going to make my math easier. 22.587 grams per centimeter cubed over 1 is the same thing. So I can put the density over 1 and it still equals the density. And now I have equivalent fractions and I can cross multiply to solve for V. So to cross multiply, 100 grams is going to equal 22.587 grams per centimeter cubed times volume. And then I can divide both sides by 22.587 grams per centimeter cubed, get the answer. Take your time, hit pause or do the cross multiplication. I'll be drinking some seltzer. Today's class brought to you by Wegmans Watermelon Seltzer. Best in the world. Here we go. So I get that, just like I said. Now, watch what happens when you divide both sides by the density. You have 100 grams is going to end up being divided by 22.587 grams per centimeter cubed. You have grams in the numerator, and then in the denominator, it's grams per centimeter cubed. So the grams will cancel numerator, denominator. The centimeters cubed on the right is in the denominator of the denominator, which means it pops into the numerator for the answer. And the answer's there in blue with 4 significant figures. This is a great problem. This, when you have to solve for volume, or if you had to solve for mass, are much more thinking problems than if you just have to solve for density. You have to write the density formula, and it helps to put the D side over 1. That way you can cross multiply. This is a great problem, right? And wouldn't it be cool to find a hunk of something, then osmium or any metal in your yard stamped 100.0 grams? It'd be like really cool. Like, where did this come from? Be a whole little mystery. Could write a short story about that. I was having a pleasant afternoon mowing the grass, and I chanced upon a shiny piece of metal stamped 100.0 grams of pure osmium. And I wondered to myself, where did that metal come from? And now the rest of the story comes out, and who knows where it will end. All right, more review. Significant figures. We're going to do the 3 on the left, then we're going to do the 3 on the right. So let's focus on the left side. 5,600 grams, 4.305 mLs, and then 0.00065 moles of Hg. Hg, what element is Hg? I'm going to take a second, all right? Happens to be my favorite element, the best element, and I am in a position to know elements. Of all elements, Hg is the best. Look for it, periodic table. I suppose it's near the middle of the table on the right side a little. It's number 80. 80. Take your time. Look at table S. Hg. You best figure that out, because if I ever ask you what is the best element, there is only one answer. All right, let's look at the significant figures. If you measured all these things, 5,600 grams, the zeros are not significant because there's no decimal point, only the 5 and the 6. In 4.305 mLs, that 0 is significant because it's between significant figures, so all of those numbers are significant. And the bottom, 0.00065 moles of mercury, the best element, the zeros on the left are called leading zeros, and they do not count. It's only 2 significant figures. So look what we got. 2 for the top, 4 for the middle, and then 2 for the mercury. Now, on the right side, it's 5.600, and that last 0 is at the end after a decimal point. So that one's significant. And then the 0 in the middle there is between significant figures, so they're all significant. In the temperature, which is just a little bit above the freezing point for water, if that was the temperature of your H2O, it would actually be in a liquid form. The 0 on the left is a leading 0, and so only the digits 6, 7, and 8 are significant. And then for the last one, 1.400 seconds, which is how long it takes to think about any of these if you're really practiced. The 0 on the far end, just like at the top, is significant, and the one in the middle is significant as well. Significant figures are significant. They're very important. They're going to come up all the time in so many calculations, in so many lab reports. It takes some time to memorize all the rules, especially around the zeros. Where are they? Are they on the leading side? Are they on the tail side? Are they in the middle? Is there a decimal? Is there not a decimal? Pain in the neck. Look like this right here. Ugh, it's a pain in the neck. You still got to learn them. It's not hard. You got to learn them. Okay. Calculate quotient. See how we're jumping around? We're jumping around. We're going from this, we're going to that. This is why chemistry sometimes is hard. Every little bit of it is easy, but there's like 814 little bits. And at any moment, this could be this one or that one, or number 411. You got to keep track of this stuff, and you got to be fast thinking, and it takes practice. It's like playing baseball. You have to practice over and over and over. Here's the ground ball to the shortstop. There's a runner at first. Throw it to second. Second baseman is to throw it to first for a double play. You practice that over and over and over. Even if you're a professional, you practice it so it becomes automatic. This is mass divided by volume. This is going to be a density problem, even though there's no formula. This number, the G, that's the mass, divided by the centimeters cubed, that's the volume. So the unit is going to be grams per centimeter cubed. So it's just math, but then the units matter. You can't just disregard the units. They're in there. And in this case, you only get two significant figures. The 2.0 only has two significant figures. 4 significant figures, let me see what my hand is, divided by 2 significant figures, that's 2 significant figures. You have to round to the correct number of significant figures. That's another rule. When you use numbers and measurements in calculations, your answer is limited to the least number of significant figures. Your answer can't be better than your worst measurement that you used in the math. Next up, we got 2 sets. We'll do the blue one first, and then we'll do the second one. Now, this is going to take more of a moment. You got to think. You got 3 temperatures, 10 Kelvin, 10 centigrade, or 10 Fahrenheit. I don't like to use Fahrenheit, but you know what temperature water freezes at. Which one of these 3 temperatures, 10K, 10C, or 10F, is the coldest or the hottest? One is the hottest, one is the coldest, and one of them, I guess, is in the middle. It doesn't matter. How are you going to do this? Well, think to yourself. 10 Kelvin, how cold is that? That's unfreaking believable cold. It's close to 0 Kelvin. It's close to absolute 0. It's almost the lowest temperature in the universe that could be possible. So 10K is going to be the coldest. Now think about 10 centigrade and 10 Fahrenheit. One of them has got to be hotter than the other one. What is the freezing point for water? Use your brain now. 0 centigrade, water freezes, or 32 Fahrenheit. 10 Fahrenheit is frozen water. 10 centigrade is liquid water. That means 10 centigrade is hotter. So out of these, the 10K is the coldest. It's near absolute 0. And the ice is melted to a liquid at 10 centigrade. Oh, look, the answers are here. I don't know why that is. I thought I had an extra slide. Sorry about that. Now, for the bottom set, water freezes 273 Kelvin. Water freezes at 32 Fahrenheit. So 280 is hotter than 32 Fahrenheit. Now, 6 degrees centigrade, that's also ice is melted. What about, we have to really compare 280 to 6. We have to do K equals C plus 273. 280K is equal to 7 centigrade, right? Or 6 degrees centigrade is equal to 279 Kelvin. So you're going to have to do a little bit of mathematics there to compare those two. They're close. 32 is frozen water. So between the 280 and the 6, the 280 is hotter. These are good questions. They're not hard. And even though we don't use Fahrenheit, you know water freezes at 32 or ice melts at 32 Fahrenheit. You can think your way through these. This is simple conversion, one-step unit conversion from grams to kilograms. You have to know, of course, that there's 1,000 grams in a kilogram. So what are we going to do here? We're going to have 125 grams on the top, and then our conversion factor, 1 kilogram over 1,000 grams. We need the grams in the denominator of the conversion factor because the grams have to cancel. And the unit we have in the numerator, kilogram, that's the one we want. When we multiply across, we have 125 over 1,000, which by calculation is 0.125 kilograms, and you have 3 significant figures. In the conversion factor, it looks like maybe there's only 1 significant figure, but that's another rule. The conversion factor has unlimited significant figures. It can be to the nth degree, literally. It could be 1.0000000 kilograms over 1,000.00000 grams. You can have as many significant figures as you want because they're equal forever. So the answer is limited to the 125, 3 significant figures. Now we got to convert liters into milliliters. Milli. You have to remember that that means 1,000. There's going to be 1,000 milliliters in a liter. So our starting point, 34.75 liters over 1. So we remember that the liters are in the numerator. And then we have a conversion factor, and we stick it in there, 1,000 mLs over liter. The liters cancel. Liters in the numerator divided by liters in the denominator equals 1, and we cancel them out. And then we multiply by 1,000 mLs. That's going to give us that big number, 34,750 milliliters, and that has 4 significant figures. If the answer had a decimal point that you could see, now there is a decimal point, but it's an invisible one. By being invisible, that 0 is not significant. But if we put the decimal point in there, it would have 5 significant figures, and that's not cool. We can only have 4. 34.75 liters has 4 significant figures. The answer is limited to 4 significant figures. So you can't write that dot in. That dot changes it from correct to incorrect. And we can't be incorrect. You got to do everything right. Here's another element, niobium. Now, if I were going to open up a nightclub, I think I would call it niobium because it just sounds so cool. Like, imagine saying this to somebody, let's meet at niobium at 11 p.m. and dance the night away. How cool is that, niobium? Okay, you measure some pure niobium metal to have a density of 8.0 grams per centimeter cube. You measure it. That's the measured value. 3 significant figures. What is your percent error? Ooh, percent error, you got to write a new formula. See how we're jumping around? Percent error is back. Write the percent error formula, and then what the heck could be the actual value? Niobium is on the periodic table, and I think it's number 42 or 43, NB. I can't see it from here. I can't see it. It's too far away. I don't have the answer. But the actual value is going to be 8.57 grams per centimeter cube. Now look at this blue text. I did not write the units in there, but they're in my head. 8.0 grams per centimeter cubed minus 8.57 grams per centimeter cubed. The unit in the numerator is still grams per centimeter cubed. Then divide those grams per centimeter cubed divided by 8.57 actual value grams per centimeter cubed. The units cancel to 1, and then it's times 100%. The answer is going to come out as a percent. And check this out. The measured value is less than the actual, it's going to be negative. So the percent error here is negative 6.65%. Your percent error, so you were off, you were under by 6.5%, 6.65% to be exact. See how we're jumping around? You got to pay attention. This is a fun class. It's like, what about this? And what about that? And what about this? You never know what's going to happen next, like a party. We're having a party here. You thought this was chemistry? No. We're having fun, F-U-N. Not everybody's having it, but everybody should. All right, do what the math says. This is new stuff again, or old stuff for you. We're going to multiply scientific notation, then we're going to divide scientific notation. Let's do the top one first. 3.5 times 10 to the 6th times 2.0 times 10 squared. You got to remember the rule. Multiply the coefficients, add up the exponents, and then make an adjustment if you have to. 3.5 times 2 is 7.0. 10 to the 6th, and then you add 2, so it's going to become 10 to the 8th. So that was really easy. Look at that. 7.0, 3.5 times 2, and then 10 to the 6th plus 10 to the 2nd. We just add the exponents to get the answer. Now for the next one, 8.0 divided by 4.0, that's division. 8 divided by 4 is 2, and we subtract the exponents. So watch, 8 minus 12, woo, we're going to be in the negative numbers. We're dividing a number by a bigger number. You're dividing a small number by a big number, you're going to get a decimal. In this case, because it's scientific notation, you have a negative exponent. When the exponent is negative, that means it's smaller than 1. It's a decimal. When the exponent is positive, like the one on top, that means it's times 10 or times 10 times 10 times 10. In that case, 8 tens in a row. That's a really big number. Exponents that are positive are big. Exponents that are negative are decimals. All right, 2 more. We got addition and subtraction. Now, both of these are tricky business. You have to change the numbers so that they both have the same exponent. Excuse me. I think I'm going to make these both 10 to the 8th. So in the next slide, I'm going to keep 3.3 times 10 to the 8th. And now I got to change the second expression. I'm going to make the 10 to the 7th bigger. I'm going to make it 10 times bigger. That means I got to make the front coefficient 10 times smaller. So I'm going to move the decimal over and make it 0.12. Instead of 1.2, I made it 10 times smaller because I made the exponent 10 times bigger. Then you just add 3.3 and plus 0.12, so you get 3.42 times 10 to the 8th. And then with two significant figures, you round it to two significant figures. On the bottom, subtraction, same kind of problem. The numbers are pretty, but they're not really lined up because 10 to the 5th is a bigger number. There's an extra column of numbers, and they don't line up neat. So in order to do this, we have to make them both, I think I made them both 10 to the 5th. But it doesn't matter. If you make them both 10 to the 4th, they'll work also, but you have to make the exponents the same. I made them both 10 to the 5th. I left the first number alone, and then the 2.33 times 10 to the 4th changes. I have to make it 10 to the 5th. That means I have to make the coefficient 10 times smaller. And then you just, in this case, subtract. And look what I did. Oh my gosh. I added them. It looks like, oh, I just got the wrong number. Look at this. What is going on? I'm going to fix this right now and see if I can't change it. I'm going to take that out. And, oh, I don't have a pen. We're going to have to fix this later. 5.64 minus 0.233. I apologize. See how I make mistakes sometimes and I don't get all worked up about it? You can make mistakes too. So to do this problem, this last one in red, 5.64 minus 0.233 equals something times 10 to the 5th. Oh my gosh, this problem is wrecked. Who the heck made this slide? We need somebody to save the teacher because he is not having a good moment with this slide. But you know what? Jimmy cracked corn and I don't care. It's just a math problem. I know how to do it. I know I made a dumb mistake. I don't have a calculator in my hand because I just fixed all these slides and I thought I had them right, but I'm a knucklehead. All right, what could you do? I think this is the last problem. If we can do this one, you should know everything about measurement. Look up the boiling point of aluminum. Now, this is weird. This can is made of aluminum and it's a solid. It's metal. If you make it hot enough, you can make it a liquid. You can melt it and pour it into a new shape. If you make it hot enough, holy cow hot, you can turn it into a gas. Now, the idea of aluminum gas is very weird for chemistry students at the beginning. Like, it's a metal, how could it be a gas? Everything in the universe can be a solid, a liquid, or a gas. It just really depends on how much energy the particles have. In this case, the particles of aluminum are atoms, and they don't have too much energy. There's so little energy, they're stuck together and they don't change shape. But if you warm them up, they start shaking a little more. They start vibrating. And if you gave them a little more energy, at some point you reach the melting point and they shake and vibrate so much they come apart and then they start moving and moving and moving. They become a liquid. And then the hotter they get, the faster and faster and faster they go. And at some point you give them so much energy, literally they explode into a gas. And you don't want to be near that because it's going to be freaking hot. And compared to the temperature of that and your body, you'll cook to a crisp in no time, right? So you can't get near gas metal. Metals don't turn into gases until crazy hot temperatures, but they're all listed in table S. So first, let's convert the temperature for the boiling point of aluminum into centigrade. And then we're going to take that centigrade temperature and turn it into scientific notation. Write the formula. Oh, back to original. One of the first formulas I gave you was converting centigrade and Kelvin. So the first thing we do is write K equals C plus 273. The number there, 2792 Kelvin, is going to equal C plus 273. To get centigrade by itself, we subtract 273 from both sides, and the C temperature is going to equal 2,519 centigrade. Now remember, water boils at 100 degrees centigrade. 100 degrees centigrade burns you bad. Your skin just gets burnt up. You stick your finger by a teapot, you get a big ugly blister on your finger in about 6 seconds and you'll cry for a week. It'll really hurt and it'll keep hurting. And then when the skin finally peels off, it'll be raw under there. It'll be hurting and hurting for 2 weeks probably. 2,519 centigrade, holy smokes. Burn your finger right off your hand. You'll never see it again. Literally crazy hot. Stay away from it. Now, let's turn this number, 4 significant figures, okay, into scientific notation. Now, there's no decimal, but we know the decimal is after the 9. We have to move it so that the coefficient is going to be greater than 1 and less than 10. So the 2,519 becomes 2.519 times 10 to the, how many places did we move the decimal? So it's going to be 2.519 times 10 to the third Kelvin. And I wrote 2792 because look at me. Who is running this show? Who is doing this to me? It's like there's a gremlin in my computer. Now, again, I don't know why I make such dopey mistakes. I don't know why. I don't know why. But I'm not going to get all excited about it. It's okay to make mistakes. But when you catch them, you fix them. Right? When I catch them, you lose a point. You say, oh, darn it. That stinks. But don't worry about numbers in boxes. They don't matter. What matters is that you learn chem. What matters is that you care. What matters is that you try and that you're good to dogs and old people and your parents and your friends. You have to be a good person. And you make stupid mistakes. I make stupid mistakes every single day. Every single day. I just fixed these slides 10 minutes ago. Right now it's like 9:35 in the morning on Wednesday. You guys are all watching that crazy video about following the rules. I spent 20 minutes making the end of the slideshow perfect. I feel great. I slept a lot. I'm drinking my watermelon seltzer, and I still make mistakes. Make mistakes. The more mistakes you make, that means the more you're trying. The more you try, and the better person you're going to be, and that's all that matters. Over and out. Measurement is done. Oh, you know what I do at every topic? Whenever we finish, look at me. Ready? I take a bow. I've done my job. Hopefully you've done your job. Do the homeworks, do the significant figure handouts, and you got to start working on those lab reports, okay? You got to start writing those lab reports. All this stuff has to be handed in, and the challenge homeworks I sent you. All right, see ya. Bye. Let's see. Stop everything. Isn't this funny? This is like the deleted scenes that they put at the end of the movie, all the silly stuff. All right.